Okay, what we're looking at here is some material from 1314D. This is will bring us to the end of 1314. We're looking at combining the chain rule with the product and the quotient rules. So we've got a few examples we're going to work through here. Our first one here, we've got this function f at x, which is x cubed times 3x minus 5 squared. And we want to take the derivative of this. The first thing we notice is that we've got two things multiplied together. So we're going to have to use the product rule. This is our u, this is our v, and so our derivative is going to be u prime times v plus u v primed. But when we look at that function v, we can see that we can regard that as a composition of two functions. It's the 3x minus 5, and then we've got the outer function, which is the whole thing squared. So when we take this derivative of v here, we are going to have to apply the chain rule to it. So we'll do this one by breaking it into parts, and then we'll put it all back together. And then for the ones that come after this, we'll just sort of do all of the derivatives right in place to see what's going on. So we've got u and we've got v here. Let's just say u is x cubed, v is 3x minus 5 all squared. U primed is pretty easy here. It's 3x squared. How do we do the derivative of v? What's the derivative of v prime going to be here?
2 bracket 3x minus 5, the product form, times the derivative set function, which is 3.
Exactly. So we bring the 2 down out in front, so we get 2 times what's inside, or the inner function stays the same, and then we got to multiply this whole thing by the derivative of the inner function, which is just going to be 3. Okay? And as we bring that 2 down, we subtract 1 from the exponent, leaving us with an exponent of 1 up there, which we sometimes don't write. So we can clean this up a little bit by multiplying the 2 and the 3 to get 6 times 3x minus 5. Okay. Now we can put all these expressions together to get the derivative of our function f. So we want f primed at x is going to be, let's see, u primed, which is 3x squared, times v, which is 3x minus 5 all squared, plus u, which is x cubed, times 6, 3x minus 5. Just put that 6 in brackets to remind ourselves that it gets multiplied by everything. Okay. Now, we want to factor this expression here. So we've got two terms, sort of split by this plus sign here in the middle, and we want to look at what we can factor out of them. So what can we factor out of these two terms that we have? We can definitely factor out a 3x plus 3x minus 5, yeah. Okay, and when we go to factor that 3x minus 5, we're looking for the lowest power of that binomial. Is there anything else that is common to those two terms that we can factor out? Factor out a 3 for sure. We can factor out x. In fact, we can factor out an x squared. So we can factor out 3x squared from both of them. So what are we going to be left with? Well, I'm going to put what we're left with in square brackets. We know we have two terms separated by a plus sign here. I've already taken the 3x squared out of there. I've taken out one 3x minus 5, so I'm left with a 3x minus 5. And then from the second term, I have factored out a 3, so that leaves me with a 2 from that 6. I factored out x squared, so that's going to leave me with an x. And, well, I've already factored out the 3x minus 5, so I don't have to worry about it. So I'm done. Except I should probably simplify what I have in the brackets here. So everything out front will stay the same, 3x minus 5. And then I've got 3x minus 5 plus 2x. So that'll be 5x minus 5. And then I notice that I can factor a 5 from the 5x minus 5, so I'll bring that out to the front and get 15x squared times 3x minus 5 times x minus 5. Sorry, x minus 1, thank you. And I'm done. Okay? So I've put this, my answer here is in as factored a form as I could possibly put it. Okay? So let's take a look at just another example here. Okay? F of x equals 4x plus 2, all cubed, and times cube root of 6x minus 7. Okay? And I want to find the derivative of this. So we'll just do this one without sort of writing out what the separate functions are. But before I start taking my derivative, what should I do to make this one a little bit easier here?
6x minus 7 is
I'm going to want to write that root as an exponent. So this will become 4x plus 2 cubed times 6x minus 7 to the exponent 1/3. Okay. Now, I'm multiplying these two things together. I've got a u and a v. I'm going to use the product rule. But both my function u and my function v are composite functions, or functions that I'm going to have to apply the chain rule to get the derivative of. So let's go to work here. First thing we want is u primed. So we're going to bring down the 3. The inner function stays inside there, and we subtract 1 from the exponent to leave us with an exponent of 2. And then we multiply that by the derivative of what's inside the brackets. So that's just all times 4. And we need to do 6x minus 7 all to the 1/3. So that is, this whole thing here is my u primed, and that's my v. To this, I want to add uv primed, so 4x plus 2 cubed is u, and now I need v primed. Well, let's see. I've got an exponent of 1/3, so I'm going to bring down the 1/3 as a coefficient out in front. I'll keep the 6x minus 7 inside, subtract 1 from my exponent, which will give me negative 2/3. And then I multiply by the derivative of what's inside the brackets. So this whole thing gets multiplied by 6. So this mess from here to here is v primed. So u prime v, u v primed. Okay. Now we want to simplify this, and we want to factor it. So just slide that up like that. So first thing I can do is I'll probably combine my my coefficients, or my constant terms, together at the front. So we'll have 12, 4x plus 2 squared, 6x minus 7 to the 1/3, plus I've got a 1/3 and a 6, so that's going to leave me with a 2, 4x plus 2 cubed, and then 6x minus 7 to the negative 2/3. And then I look for what I can factor out of this. So let's look at the constant terms, or the coefficient terms first. 12 and 2, I can factor out a 2. I can factor out 4x plus 2 is common to both of them, so I look for the lowest power, which is going to be 4x plus 2 squared. And then I look at, I've got a 6x minus 7, which is common. And again, I look for the lowest power, which is going to be negative 2/3. So that's what I can factor out. What am I going to have left after I do that factoring? Well, I'm going to have two terms separated by a plus sign. And let's just go through it term by term here. So I've factored out the 2 from the 12, so that's going to leave me with a 6. 4x plus 2 squared. I've taken out 4x plus 2 squared, so I don't have any of that left. And I've got 6x minus 7 to the 1/3. I'm dividing by 6x minus 7 to the negative 2/3, which is going to leave me 6x minus 7 to the 3/3, because I'm adding 1/3 plus 2/3. So I'm just going to have 6x minus 7 there. For the second one, let's see, I've already factored out the 2. I've factored out 4x plus 2 squared, so I'm going to be left with a 4x plus 2. And I've already factored out the entire 6x minus 7 to the negative 2/3. So there, I'm done. Now, I'm going to want to clean this up a bit. So I'll keep the 2 and the 4x plus 2 squared. This 6x minus 7 to the negative 2/3, I can move down to the denominator by changing my exponent to a positive exponent. And now I want to expand and simplify what I have in the square brackets here. So 6x times 6x, 6 times 6x is 36x minus 42 plus 4x plus 2 in the square brackets. And then I can simplify what I have in here. Let's see. And all the rest of this mess stays the same. (40x minus 40). Okay, and that looks like that's going to factor as well. 6x minus 7 to the 2/3. So I can factor out a 40 from the square bracket. So bring that 40 out front, multiply it by the 2, and I've got 80, 4x plus 2 squared times x minus 1 all over 6x minus 7 to the 2/3. And that's as factored as it's going to get.
That's like the final simplified form.
Yep.
Wouldn't like square forms as well.
I wouldn't expand that, no. Because, I mean, usually I want these things in factored form, so I could say set it equal to 0 and find the zeros, which would involve factoring again. Okay. All right, let's do one more example here, except this time we've got something that involves the quotient rule. Okay, so we got something over something using the quotient rule. Yeah. Yeah, this is the trick. If you're like me and you don't like really using the quotient rule because you find it's overly complicated, you can take ones that should involve the quotient rule and turn them into questions that you can answer using the power rule. Sorry, not the power rule, the product rule. So I can take this x minus 2 to the power of 3, and I can take it out of the denominator and bring it up into the numerator by changing the exponent to a negative. So I can rewrite this as 2x minus 1 squared times x minus 2 to the negative 3. Now this becomes just like the questions that we've just done. Okay? This is a common trick just because a lot of people find the product rule easier to use than the quotient rule. So now we can take our derivative here. We've got u and v. So we want to do u prime times v. So 2 times 2x minus 1 to the power of 1 times the derivative of what's inside. So times 2 is our u primed. And we want to multiply that by x minus 2 all to the negative 3. That's our v. To this we want to add our u, 2x minus 1 squared, times the derivative of v. So we bring down the negative 3. We've got x minus 2 to the negative 4 now, and we multiply by the derivative of what's inside, which is just 1. So we've got, let's see, u primed v, u, v primed. What do I want to do from here? Well, we've got to look. For this one, I think we can sort of start simplifying here. So we're going to have 4, 2x minus 1, x minus 2 to the negative 3, plus, but it's not going to be plus because we've got negative 3 times 1 there. So our coefficient is going to be negative 3 times 2x minus 1 squared times x minus 2 to the negative 4. And now we want to factor. So what can we factor out of these two guys? Nick?
X minus 1 and x minus 2 to the power of negative 1.
For sure. 2x minus 1, it's common to both of them. We look for the lowest power. And for the x minus 2, again, we look for the lowest power. So it's going to be the negative to the exponent negative 4 that we factor out. What are we going to be left with after we factor those things out? Well, two terms separated by a minus sign. We haven't factored out a coefficient here, so I'm going to have a coefficient of 4 here and a coefficient of 3 there. And in our first term, let's see, I've taken care of the 2x minus 1, so I'm just going to, let's see, x to the negative 2, x minus 2 to the power of negative 3 plus, I've got to add the exponents, so I'll be left with x minus 2. And in the second one, I factored out 2x minus 1, so I'm left with a 2x minus 1. And I've already taken care of the x minus 2 to the negative 4. So let's simplify this. I'm going to have 2x minus 1. I can move the x minus 2 to the power of 4 down to the denominator. And we want to expand and simplify what we have in the brackets here. So that's going to be, let's see, 4x minus 6x. So negative 2x, negative 8 plus 3, negative 5. And there we are, completely factored. And notice that down in the denominator, I've got x minus 2 to the power of 4. In our original function, we had x minus 2 to the power of 3. Okay, so had we used the quotient rule, we would have squared that, but then we've got a bunch of things that are canceling out to bring this down to x minus 2 to the power of 4. Okay. So if you're given a question like that, you have the option. You can use the quotient rule, you can use the product rule, whichever one you find easier. Austin?
Should we bother factoring up?
I wouldn't insist on it. If there was something you could factor out of there, like let's say it was negative 2x minus 6 and you're factoring out the 2, it's probably a good idea to factor out negative 2 instead, but I'm not going to insist on it. Okay?
So say you did factor out a negative 1 and you wanted to do the chart, like the integral chart, the first derivative test, you would keep the negative 1 as a negative number.
It would be a negative constant out in front.
Yeah.
Yeah. So yeah, that's where it's going to help you if you're setting up the interval chart. Gives you another term to check the sign with, or you can keep track of it like this. Okay. So that's straightforward. What the guide covers mostly is it gives you a lot of practice working with those kinds of questions. Here's a slightly different kind of question involving, well, it's a little bit more abstract here. So we're given a function, f at x, in terms of x, and we've got some other function thrown in there, g at x. Okay? And we want to find an expression for f primed at x that is going to use g at x and g primed at x. So really what we're asked to do here is work with those derivative rules in cases where we don't really know what the function is. So just kind of work with the definitions a little bit. So the first one's pretty straightforward here. F at x equals x cubed times g at x. What rule are you going to have to use to take this derivative here, f prime at x? The product rule, right? Because these two things are multiplied together. So I know that my derivative is going to be the derivative of my first term here, or my u, which is going to be 3x squared, times my second function, or my v function. I'll just label these u and v, just so we know what we're talking about. So times v. Now, I don't know what v is, so I'm just going to keep it as g at x. To this, I'm going to add my u function, x cubed. And what do I have to multiply x cubed by, or u by, if we're using the product rule? Yeah. Well, not g of x, g prime at x. I want the derivative of that v function, so I've got to multiply it by g prime at x. Now, I don't know what g at x is, and I don't know what g prime at x is, but I can just keep them in there as, like it says in the question, g at x and g prime at x. So let's take a look at the second one here. F at x equals g at 4x squared plus 2x minus 1. What rule am I going to have to use here in order to get f prime at x? Yeah, it's composite function, so I'm going to have to use the chain rule here. So what is the chain rule going to look like? Well, remember, our chain rule is if we've got if f, let's just say, our chain rule was that if we had f at x equals some function, g is a function of u, our derivative was going to be g primed at u times u primed. Okay? So how can we apply that in this situation here? Well, what we need first is we need g primed evaluated at that inner function. We don't know what g primed is going to look like, so all we can really say here is this is going to be g primed at 4x squared plus 2x minus 1. And then we have to multiply this by, well, what do we have to multiply it by? Which is going to be plus 2. Because that's the derivative of the inside function. Okay? So again, we don't know what g primed is, and we can't simplify that at all, but we can just leave it as g primed. Okay, so here's the tricky one. F at x equals the square root of g at x squared plus 2x squared plus 3. We want to find the derivative here. What would you do first? Let's do that first. So this will become g at x squared plus 2x squared plus 3 all to the exponent 1/2. Well, f prime at x is what we want. Okay. This involves doing the chain rule twice. What's our outermost function here? Let's start on the outside and work our way in. Yeah, it's the 1/2. So let's do the derivative of that 1/2 thing. So we bring down the exponent. In brackets, we keep everything the same. G at x squared plus 2x squared plus 3. And our new exponent is to the negative 1/2. This is chain rule, right? So we've got to take the derivative. We've got to multiply that by the derivative of what's inside. So inside the brackets, we have three things. We've got g at x squared, we've got plus 2x squared, plus 3. So we want the derivative of this plus the derivative of this plus the derivative of this. That was the old sum rule that we looked at. So let's start with the first thing. How do we do the derivative of g at x squared? To get that derivative, we need to use the chain rule because it's actually a composite function. So we can do that as g primed at x squared times the derivative of our inner function, which is 2x. The derivative of the x squared, right? Then that takes care of that first term. Now we can do the derivative of the second term, which is 2x squared. Well, the derivative of that is going to be 4x. And fortunately for me, the derivative of the last term is just 0, because I don't have any room left in my brackets. But that would be my final expression. Okay? And that was the tricky part on this one, is applying the chain rule after I'd already applied the chain rule. Okay? Where would I do the product rule? There's multiplication right here. This multiplication, though, comes from applying the chain rule. Yeah. Yeah. Which term on the bottom? Yeah, you're right. I could clean this up by doing, let's see. How could I clean this up? Okay, g primed at x squared is going to go on top times 2x plus 4x, okay? And then down on the bottom, I'm going to have 2, and then the square root of g at x squared plus 2x squared plus 3. Does that work? Okay. Now, if I wanted to get really fancy, what I could notice is that this thing right here is actually the same as my original function. So I could, if I wanted to, write this as g primed at x squared times 2x plus 4x all over 2 times f at x, expressing my derivative in terms of the original function. You usually don't do that unless you're asked to do that in the question. If they say express it, and here they only asked us to express it in terms of g at x and g primed at x, so I probably shouldn't do that in terms of the original function f at x. So likely you would stop here. Stop. Okay. That is it.